Hi, this is Maria, and I'm going to talk to you about intermolecular forces. So the goals for our video, briefly reviewing polarity, and to introduce the three intermolecular forces important in this class: London dispersion forces, dipole-dipole, and hydrogen bonding. So just a brief review of polarity itself. So remember, a polar molecule has essentially areas of partial positive charge and partial negative charge. And remember, to determine polarity, you ask yourself essentially two questions. First question, does the molecule contain polar covalent bonds? If so, awesome. Move on to the next question. If not, you do not have a polar molecule. And then the second question is, just ask yourself, is the molecule symmetrical? So if the molecule is symmetrical, yes, well, then you have a nonpolar molecule. And no, the molecule itself is polar. So think of it honestly like a flowchart. You could really organize this into a flowchart as well. We're going to do a little practice with this before we move on. If you take a look at dinitrogen over here. So you have essentially nitrogen bonded to nitrogen. Well, what's the electronegativity difference going to be on that? Well, 0. So we should have a not polar molecule, a non-polar molecule. That's exactly it, right? You see just a gray cloud around here. So that's smack in the middle of the electrostatic potential. It's pretty darn neutral. All right, let's think about another molecule. So if we're thinking about fluoromethane, which is CH3F, there's one F, 3 H's, 1 carbon. All right, cool. Let's think about this. Well, if I look at the electronegativity difference for each of those hydrogens to carbon, it's pretty small. It's only 0.4. So that's in the nonpolar region. But what about carbon to fluorine? Well, fluorine is the most electronegative atom in there. So if you are looking at fluorine, remember that's at about 4. And when we're talking about carbon, that's about 2.5. So that's a pretty big difference. 1.5, this is definitely a polar covalent bond. So let's move on to the next question. Is this symmetrical? I would say no. Not symmetrical unless we're talking about this plane. All the other planes are not, it's not going to work. Not symmetrical. Let's take a look. Definitely got an area of negative charge and some area of positive charge as well. All right, so this is definitely a polar molecule. Let's think about this guy. So I have carbon bonded to essentially 4 fluorines. Well, we just talked about that. That has a pretty large electronegativity difference for each of those bonds. Okay. But is this symmetrical? This is where it gets a little trickier, right? Yeah, it's somewhat symmetrical. And especially if you draw the Lewis structure, you'd be like, that's definitely symmetrical. So if you end up looking at this particular one, you'll notice that this is a pretty nonpolar molecule, but it does have very tiniest amounts of slightly negative areas and slightly positive areas. Okay. All right, so that should have reviewed a little bit about polarity, but there's one more thing I want to point out before I move on. Polarity is on a spectrum. We're going to talk about pretty small molecules in this class. We're really going to talk about where maybe there's a few central atoms, but it is on a spectrum. You can have large molecules that have polar parts and nonpolar parts. So as somebody who teaches biology, I just want to give you a preview for next year. So if you're thinking about this, this looks horrifying. I know, you would never be asked to draw this. This is actually what's called a phospholipid. And so when we're thinking about this particular molecule, you can see there's a lot of carbon-hydrogen bonds. We know those are nonpolar bonds. All right. But then there's some other trickier stuff over here. So there's some really polar portions over here, especially this particular spot. And then this is really not polar. So it's just a kind of interesting thing to think about. Its polarity is on a spectrum. You can have polar parts in some part of a molecule and nonpolar parts in another part. All right, let's move on to our main event. So intermolecular forces. The most important thing about it's honestly forces between molecules. You can think the word international, right? When I'm talking international, I'm talking between different countries. That's a really helpful thing to think about. There is also something called intramolecular forces, but we don't really care about those for this class. They're important, but not quite as important as intermolecular forces. So the dashed lines here are sort of showing, oh, there's some forces between these molecules, and then there's technically some forces between here. For intramolecular forces, the only thing that you really would call them at this point are things like the bonds that we've discussed in class. Other than that, we don't care. All right, London dispersion forces. So this is the first one we're going to talk about. It's found in all molecules. It is a very, very weak particular force, and it's incredibly temporary. And it essentially forms what's called a dipole. And we've used this word in class before, but it's just this idea that there is an uneven distribution of electrons in one thing or another. So in this particular example down here, you've got the helium atom. And so if I have this uneven distribution of electrons, and in this helium atom, and it's near this other helium atom where it was like, oh, it didn't have any uneven distribution of electrons. Well, if this is close to this, well, you can imagine that this positive charge is going to have an effect on the electrons over here. So you would end up having this idea that, oh, there's going to be some negative charge over here. And then because all the electrons are running over there, there's going to maybe be some partial positive charge over here. So essentially it's this idea that there's an induced dipole on that neighboring atom. And it's easier to visualize with one atom, but this also happens with many molecules. But just keep this in mind. It's found in all molecules. All right, dipole-dipole interactions. This is where we get a little more specific. It's found only in molecules that are polar. It is stronger than LDF because it's not a temporary force. This is something that actually lasts much longer. All it really is just an electrostatic attraction, which we've talked about before in class. We have a partial positive side in a molecule. It's attracted to the partial negative side in a second molecule. So if I'm looking at this chlorine here as a partial negative charge, well, it's actually attracted to the partial positive charge in this hydrogen. Awesome. Okay, now this is the biggest one and the most important one to really, really, really understand. So hydrogen bonding interactions. So hydrogen bonds are found only in molecules. They must be polar, and they must have a hydrogen directly attached to either a nitrogen, an oxygen, or fluorine. It's the strongest out of the three, and it's essentially just a special version of dipole-dipole. It's dipole-dipole, but it's just much, much, much stronger because of the hydrogen being attached to either nitrogen, oxygen, or fluorine. You're welcome to think about why that is about nitrogen, oxygen, or fluorine. What do we know especially about things like fluorine, maybe oxygen, maybe nitrogen? Some cool things to think about. Maybe ask your teacher. All right, so I just wanted to show you guys. So, of course, water is our favorite thing to talk about for hydrogen bonding interactions. Remember when we're talking about water, if you've seen this before, you've probably seen this sort of like Mickey Mouse looking diagram where you have the hydrogens as representing as white and the oxygens being represented as a red sphere. So remember that on the oxygen itself, it's got partial negative charge, and on the hydrogens, you've got that partial positive charge, and there's just the attraction between the different molecules. Okay, seems simple enough. I need you to know this. Hydrogen bonding is not an actual bond. I know, the name is super misleading, but it's an attraction. It's an intermolecular force, not a bond. I'm really sorry about the fact that the name is so misleading. Both Becky and I would choose a completely different name. But please keep this in mind. It is not a bond. Another common mistake is also to refer to the bond within the molecule as the hydrogen bond, because you're like, oh, it's a hydrogen bonded to something. We're talking about intermolecular forces. We are not talking about bonds. This is a covalent bond. The attraction between this hydrogen on this molecule and the oxygen on this water molecule is the hydrogen bond. Please do not call this a hydrogen bond. It's not. We're talking about intermolecular forces, different molecules. Okay. So I just told you a bunch of things. Why do we actually care? Well, you're going to end up finding, because you'll watch another video and we'll talk about this in class, that the types of intermolecular forces present in a compound lead to properties. And so at this point, we've kind of painted this picture. We've got Lewis structures. We talked about the shape of the molecule through when we were talking about specifically molecular geometry. And that shape of the molecule gets to influence polarity. And then polarity definitely influences what types of intermolecular forces you have, and what types of intermolecular forces you have influences your properties. So we'll talk about this more in a future video, so we'll definitely discuss them. All right. Please remember to try this. Try this, try this, try this. Okay, so what I'd like for you to do is go and draw the Lewis structure, determine the molecular geometry on the center atom, and then using both of those things, I want you to think about whether something's polar or not. I know, it's a little tricky. Make sure you identify what types of intermolecular forces are present in the molecule. And I'd like you to do this for two things. I'd like you to do this for hydrogen cyanide, and I would like you to do this for ammonia. All right, that's it for tonight, and I'll see you tomorrow. Feel free to ask questions during class for anything that you're confused on.